Welcome back, everybody. Learning as a hobby here. I'm going to go through my summary for section 4.3 and analysis 1 by Terrence Tao. So that's what this video is. It's shorter than I thought that it was going to be. So actually, this video is probably going to be not very long. The exercise set also for this section is not very long, and neither is actually, for that matter, the next section or its problem set. So we should be, we're on track to getting chapter 4 done this week, actually. So let me get to my notes so we can go through it, and then hopefully today I'll have time to work on the exercise set. All right, so here are the notes, my summary for section 4.3. We start by defining absolute value. What this section is doing is sort of setting up the machinery that we need in order to study what it means for points to be close to each other, sort of motivating like limits and things like that we need for when we get to Cauchy sequences in the next section when we construct the real numbers. At least that's the way the Tau does it. So that's what we're building up here. So in order to do that, we need the notion of absolute value of a number. So here's definition 4.3.1. If x is a rational number, the absolute value of x, which is a familiar notation, I hope, x with the bars around it, is defined as follows. If x is positive, then the absolute value of x is just x itself. If x is negative, then the absolute value of x is the negative of x. And if x is 0, then the absolute value of x is just 0. Right? And with that, we can define the notion of distance between 2 points. Let x and y be rational numbers. The quantity absolute value x minus y is called the distance between x and y and is sometimes denoted dxy. Thus, dxy is defined to be equal to the absolute value of x minus y. So we need this notion of distance, like I said, to be able to talk about when points are close to each other. Okay, then we have some propositions here. The first proposition, 4.3.3, is on basic properties of absolute value and also the distance function defined on the rationals. So let x, y, and z be rational numbers. Then there's a bunch of properties here. And we're going to be I mentioned at the beginning, I said the exercise set for this section is kind of short, but a lot of the theorems that he's going to ask us to prove have a lot of parts to them. So it might be deceptively short looking, the problems, but it's still not that many problems. Anyway, part A, non-degeneracy of absolute value. So we have that the absolute value of any rational number is always non-negative, and also it's 0 if and only if the number x is equal to 0. All right, part B, we have the triangle inequality for absolute value. We've actually seen the triangle inequality in Spivak a while back, in the early parts of the book, but we need it here as well. We have absolute value x plus y is always less than or equal to the absolute value of x plus the absolute value of y. All right, part C, we have the inequalities negative y less than or equal to x less than or equal to y if and only if y is greater than or equal to the absolute value of x. In particular, we have that the negative absolute value of x is less than or equal to x, which is less than or equal to the absolute value of x. All these inequalities are going to be useful when we get to limits and so on. Part D, multiplicativity of absolute value. We have absolute value xy equals absolute value x times absolute value y. In particular, the absolute value of negative x is the same number as the absolute value of x. All right, and then we have some similar definitions for distance, properties for distance. First thing is part E, the non-degeneracy of distance. We have the distance between any two rational numbers is always non-negative, and the distance between any two rational numbers is 0 if and only if x is equal to y. All right, part F, the distance function is symmetric, so the distance between x and y is the same distance as the distance between y and x. And then also we have a triangle inequality for the distance function. The distance between x and z is always less than or equal to the distance between x and y plus the distance between y and z. All right, and the proof we'll do in the exercise set. So you'll have to wait till that next video, which hopefully I'll be able to have out tomorrow. So see exercise 4.3.1 when we get to that. Right, then we need another definition here, which he calls epsilon closeness. I think Spivak used similar terminology when in one of the sections that we looked at when we were looking at limits in Spivak. But anyway, this is definition 4.3.4. Let epsilon greater than 0 be a rational number, and let xy be rational numbers. We say that y is epsilon close to x if and only if we have the distance between x and y is less than or equal to epsilon. Right, and then he has a remark here that he labels 4.3.5. The above definition, 4.3.4, is not standard in mathematics. We will use it as what he says, quote unquote, scaffolding to construct more important notions of limits, and in the next chapter of Cauchy sequences later on. Then we'll discard the notion of epsilon close because we'll have limits and so on. Right, he gives an example too, just to get give a more concrete sense of what epsilon close means. The numbers 0.99 and 1.01 are 0.1 close, but not 0.01 close, because the distance between 0.99 and 1.01 is equal to 0.02, which is larger than 0.01. The numbers 2 and 2, the same number, are epsilon close for every positive epsilon. All right, then we have a proposition here. Let x, y, z, w be rational numbers. Then we have some properties here of that involve the notion of epsilon closeness. Part A, if x equals y, then x is epsilon close to y for every epsilon greater than 0. Conversely, if x is epsilon close to y for every epsilon greater than 0, then we have x equals y. All right, part B, let epsilon be greater than 0. If x is epsilon close to y, then y is epsilon close to x. If let epsilon and delta be greater than 0, if x is epsilon close to y, y is delta close to z, then x and z are epsilon plus delta close. These first three parts here, A through C, should remind you a little bit of reflexivity, symmetry, and transitivity. He makes a note about this later, but just keep that in mind. Part D, let epsilon delta greater than 0. If x and y are epsilon close and z and w are delta close, then x plus z and y plus w are epsilon plus delta close, and x minus z and y minus w are also epsilon plus delta close. Part E, let epsilon greater than 0. If x and y are epsilon close, then they are also if epsilon greater than 0, if x and y are epsilon close, then they are also epsilon prime close for every epsilon prime greater than epsilon. I don't know why that was so hard for me to read. Part F, let epsilon greater than 0 if y and z are both epsilon close to x and w is between y and z. In other words, y is less than or equal to w, less than or equal to z, or the other way around. Then w is also epsilon close to x. Part G, let epsilon greater than 0 if x and y are epsilon close and z is non-zero, then xz and yz are epsilon times the absolute value of z close. And then finally, the last property here in this proposition, let epsilon delta greater than 0. If x and y are epsilon close and z and w are delta close, then xz and yw are epsilon times absolute value z plus delta times absolute value x plus epsilon delta close. And so that there's all these properties here. He asks us to prove this in the exercise set, so we'll do that in the next video. Like I said, these propositions have a lot of parts, so the size, in the book of the exercise set might be deceptively small. I think I'll still be able to get it done by tomorrow, though. Anyway, I keep going back to that point, but he has a remark here after that proposition, 4.3.8. It's often useful to think of the notion of epsilon close as an approximate substitution for that of equality in analysis, which is what I mentioned a second ago. Compare statements A through C of the proposition that we just read with the reflexive, symmetric, and transitive axioms of equality. And then just a note, we now recursively define exponentiation for natural number exponents, extending the previous definition all the way that we looked at all the way back in chapter 2, which was definition 2.3.11. All right, so here this is definition 4.3.9, exponentiation to a natural number. Let x be a rational number. To raise x to the power 0, we define x to the 0 to be equal to 1. In particular, we define 0 to the 0 power to be equal to 1. And now suppose inductively that x to the n has been defined for some natural number n, then we define x to the n plus 1 to be x to the n times x. So it's a recursive definition. Then we have some properties involving exponentiation to natural number powers. He labels this proposition 4.3.10 properties of exponentiation part 1, because we'll in a second we'll look at properties part 2. Let x, y be rational numbers, and let n, m be natural numbers. There's 4 properties here that you should be familiar with. Properties of familiar properties of exponentiation. We have x to the n times x to the m is x to the n plus m. X to the n raised to the m power is x to the n m power, and x to the xy to the n power is x to the n times x to the n. So exponentiation distributes over products. Part B, suppose n greater than 0, then we have x to the n is 0 if and only if x is 0. Property C, if x greater than equal y greater than equal 0, then x to the n greater than or equal to y to the n greater than or equal to 0. In other words, the order is preserved. If x greater than y greater than or equal to 0 and n greater than 0, then x to the n greater than y to the n greater than or equal to 0. And then finally, if we have the absolute value of x to the n, that's equal to the absolute value of x to the n. And again, we'll prove this in the exercise set. So that'll be exercise 4.3.3. All right, and now we actually extend that even further. Definition 4.3.11, we define exponentiation not just to natural number powers now, but to negative numbers. So let x be a non-zero rational number. Then for any negative integer negative n, we define x to the minus n to be the rational number 1 over x to the n. And then there's a note, the following properties that we'll look at below, which is properties of exponentiation part 2, supersede proposition 4.3.10, which we just looked at. So there's very similar properties here, but I'll read them out anyway. Proposition 4.3.12 says let x, y be non-zero rational numbers, and let n, m be integers. Then we have 4 properties. The first one is similar to the first one in the previous proposition. Second one is similar as well, except if n is negative, the order of the order gets reversed. So maybe I should read it out anyway. If x greater than or equal y greater than 0, then x to the n greater than or equal y to the n greater than 0 if n is positive, and 0 less than x to the n less than or equal y to the n if n is negative. So like I said, if you exponentiate to a negative exponent, you have to reverse the order of the inequality. Part C, if xy greater than 0 and not 0, and x to the n equals y to the n, then x equals y. Notice here x, y have to be positive for this to work. And part D, we have the absolute value of x to the n equals the absolute value of x raised to the n power. And again, this is a proposition that we'll have to wait to prove in the exercise set. That'll be exercise 4.3.4. And I guess that's it. So that's like I said, it's actually kind of short, this section. I thought it was longer than it actually is. So let me stop the screen share. So really, all of the work for this section is going to be done in the exercise set, which I'll, like I said, try to have posted by tomorrow. I'll see you guys in that video, so keep learning. Actually, I have some vlogs and stuff coming up soon too, but I'll talk about that when they come out. So keep learning, guys. I'll see you in the next one.